morning. So let's start on a new topic altogether. And after finishing top-down plotting, let's start looking at what is bottom-up parsing. These are the two methods we are talking about. So bottom-up parsing is the method where you start constructing the parse tree from the leaf nodes and then try to reduce the whole of the string to the start symbol. And if we succeed in that, then we say that the string belongs to the language which is specified by the language, by the grammar. Okay. So in this case, you want to construct the parse tree from the input, which means that the leaf nodes. Okay. Or another way to look at it is that if I say that W is a valid string in the language which is specified, then I should be able to somehow reduce W to the start symbol. This is another way of saying same thing. So let's look at a grammar, and then let's also, so here is a grammar where I have the start symbol S. So here is a grammar where we have a start symbol, and then corresponding to the production of non-terminal A, I have two rules, and then I have one more rule for B. Okay. And then here is a string I want to parse. So let's take this grammar and try to see whether this string belongs to the language which is specified by the grammar. And how do we go about doing it? What we want to do is we want to reduce the string to the start symbol. So what we'll try to do is we'll try to find out a substring here which matches right hand side of a production. And if it matches right hand side of a production, then I'm going to replace that by its left hand side, and we'll continue. And hope is that if this is a valid string in the language specified by this grammar, then I should be able to reduce the whole thing eventually to S. Right? So the first thing I do is I say that here is B, which matches right hand side of a production which says A goes to B. So I replace this by A, and after reduction, my string becomes, now this becomes now a sequential form. Okay. Now again, I look through this and I find there is another B. So I just go ahead and try to replace that by its left hand side. And when I do that, okay, I get string like this. Okay. Now let's again try to see if I can find a pattern on the right hand side. So you notice something, A, C, D. D matches now. So D can match perhaps this right hand side. Okay. And if I replace that by B, what will happen? So I am replacing this by D. I reach here. Now how do I proceed from this point? Can you find a pattern on the right hand side which in this string which matches right hand side of one of the productions? No. So it appears that the choices I made, okay, took me to a situation where we said that this string actually to begin with does not belong to the language which is specified by this grammar. May I request everyone that from next class onwards, either you reach here on time, you know that there's a class at 9, there is no reason to plan. I mean, you know that you can plan everything 5 minutes earlier. So either reach here on time or don't come to this class. I mean, it really disturbs. We have a 50-minute class, of which we have already spent 7 minutes, and people are still coming in. And I'm sure, I mean, next 5 to 10 minutes, this will keep on happening. I mean, you know that there's a class at 9. I mean, I can't understand why you cannot come at 9. I mean, if you wake up at 6:30, if you wake up at 6, if you wake up at 8, wake up 5 minutes before that and reach here at 9. I mean, I don't see any problem in doing that. But this habitual habit of saying that if there's a class at 9, I can always stretch it to 9:10. If there's a class at 12, I can stretch it to 12:10. If the class is at 2, then I can stretch it to 2:10. It's just not an acceptable situation to do. Okay? So next class onwards, make sure either you're here on time or you're not here. Alright, so when we started making these choices, okay, so at some point of time, suppose I made slightly different choices. Okay. then let's see what could have happened. Okay. So when I was, so rather than going in this direction, let me just keep this here and try to write rest of the strings on this side. And when I say that this reduction happens, okay, to A, I am going to this situation. Okay. And now when I made this choice, I was saying that match this B as the right hand side. Instead of that, I make a different choice. And I say make this, match this ABC, which is right hand side of a production, and then replace it by its left hand side. So if I do that, I'm going to get a string like this. And now again, if I look at right hand side pattern here, which is B, which matches right hand side of a production like this gives me B. Okay, and I get a string like this, and this matches now right hand side of the first production, the whole thing, and therefore I reach the start center. Okay, and therefore I can conclude that the string I started with is a valid string in the language. Okay, I can show it from this string, these steps, but only problem which happened in this part was that at some point of time, rather than making this as a choice of matching, I made this as a choice. Right? Now that's an issue. Okay? So the same thing, like if you recall, we were saying at some point of time when we were doing top-down parsing, that there were two issues: which production to use and which non-terminal to expand. Here the issue is going to be which substring to match, okay? And if I have more than one choices, then somehow I need to find a strong enough method of doing this kind of reduction, okay? Which will always identify that this is the right string and this is not the right string to match. Okay? So this is what going to be the part of building the bottom-up parser, that when we process this grammar, somehow this information will be captured here. Okay? So is this point clear, that two different choices can lead to a situation which are entirely different from each other? Okay? So this is what is captured here. Okay? But let me also simultaneously observe, okay, that if I look at this complete reduction and I also look at the rightmost derivation of the string starting from S, okay, then I actually am doing a derivation which is not leftmost but rightmost. Leftmost was what we did in top down, and it gives me the same string. Okay. And now if you see the steps here, okay, this actually is the rightmost derivation. That means what I am doing is I am going in reverse of rightmost derivation. Okay. Now I won't go into the proof of saying that if you are building a bottom-up parser, then the reduction has to be in the reverse of rightmost derivation. That is a result you will have to take for granted. I am not going to discuss the proof of that. But this information somehow will be captured when we start constructing the parser for grammars like this. When we start constructing a bottom-up parser for grammars like this. That bottom-up parsers are really the reverse of rightmost derivation. Okay. Now, these are also traditionally known as shift-reduce parsers. Okay. Now, shift-reduce, somehow, I mean, you can get this feeling that when you're talking of shift-reduce parser, you need to use a stack. But basically what that means is that I can take any string, okay, and when I say that I am taking a string like this and I want to do a reduction, conceptually I can see that there's some parts I have seen, and once I have seen some part, then I am doing a reduction. Okay? So let's put some imaginary symbol in middle of a string and let me call it dot, and then we say that two parts which are separated by the special symbol dot, when we say that because I am doing now a reverse of rightmost derivation, then the left hand side of dot is going to be a string of terminals and non-terminals, and right part of what is on the right of the dot is always going to be a string of terminals. Okay? So look here what is happening. Okay? If I say this is the derivation I am doing, then first I derive this, then from this D I derive this, then from A I derive this, and then from this A I derive this. Okay? So at any point of time what was happening, that I was saying that I will be somewhere here, and then I said that I am going to replace this, then my dot must have been what I was just reducing here, then this dot must have been here, and then this dot must have been here. Okay. Now imagine that somehow this dot appeared in these positions in my string. Then what was going on? Okay. What was going on was that if you now see the right hand side of the dot, you only have either a null, which is the final state, and you are going to have only a string of terminals here, but what you have on the left hand side is a string of terminals and non-terminals. So basically one way to visualize this is, my start state is that I will always start, when I say that I am beginning, this is where I started with, that to begin with my dot will be here, and then I'll say I'll keep on shifting this dot along the string. Okay. So let me pick up another example and keep this example alive so that we can do this comparison. But basically what we are doing here is that at any point of time, if I say that this is the kind of configuration I have, okay, something like this. Okay. So what this configuration is telling you is that I have some string of terminals and non-terminals on left of dot, and what I have on the right hand side are basically just a string of terminals. Okay. And now when I say that I have something called a shift action says that the symbol which is immediately on the right of dot must be shifted to the left of dot. Okay. So my configuration after this is going to be something like this, or if you are confusing W with the whole string, let me just replace this by R. Okay. My configuration will be something like this. And what will be reduce action? Reduce action is saying, now see the example there, that if you see something which is immediately on the left of dot and which is matching the right hand side of the production, then we say that I am going to do a reduce action. Okay. So reduce action is saying that if this part of this starting from here matches right hand side of the production, match that and replace it by its left hand side. Okay. Now let me also sort of alert you that when you talk of a bottom-up parser is not as intuitive as the top-down parser. In top-down parser, what you could see immediately was that you were starting from start symbol, and by having a look ahead of 1, you were able to figure out which production to use. Okay. Bottom-up parser to begin with will be slightly non-intuitive, but as you get into it, you will start getting the concept and you will start getting the visualization. So be alert on this part, that somehow you will find that this imaginary position of dot is going to create a lot of confusion till we really give the definitions. Okay? So initially, my input is that dot is on the left hand side of the string I am trying to match, and what is the final position? Final position is going to be that on the right hand side of dot is going to be null, and on the left hand side of dot is going to be start symbol. Okay? So my final position is going to be something like this, which is here. Okay? And initial position is going to be something here. And then I have to see that what are the situations under which I do a shift and what are the situations under which I do a reduce. So for example, in this case I said that do a reduce, take it to B, but when I shifted dot here, then I was saying don't do a reduce here, okay, but keep on shifting and then do a reduce. Okay, so you have a choice between doing either a shift or doing a reduce. Blank faces. I can see it's not making sense. Okay, so raise questions. So what is the problem? What is it that at least in this part we have not understood? Magically how dot is shifting. Is that the sort of issue which is creating problem in everyone's mind?
So by reduction, you mean the longest terminal is the longest stable match? Or
no, nothing. I have not said anything.
So in that case, when we first reduce A, in both the cases.
This side or this side?
Yes, on both the cases.
Okay.
When the dot is on A, on the right side of A.
Okay. No, dot is not on the right hand side of A. Dot is on the right side of B. And then I said that whatever is on the left hand, immediately left hand side, starting from this position, it matches right hand side of a pattern, and I reduce that to A. So either I could come here or come here.
So now in the next step, the dot will come on the right side of B.
So dot will come here, or dot will come here.
So in the down you reduce B to capital A, and in the other one you again shift it. So
Yes.
means why not reduce there and why reduce?
Exactly. So question is that if I have a choice and the choice is saying that I do a shift or reduce. Okay? One of the choices led me to a wrong conclusion saying string does not belong to the language specified by the grammar. Okay? But this choice made sense because I could reach my start symbol. Okay? So my parsing method should make sure that I am always making the right choices.
So how did we decide that right choice?
So that is what the parsing method is going to be all about. So as I said, right now there is some magic happening. Okay? Like we did in top-down parsing, we said somehow I am going to use this rule for production. Which rule? That I defined much later. Right? So I computed all these first and follow sets, and then I was able to pin down that if this is the non-terminal for expansion and this is the look-ahead symbol, then use this rule. Okay? Similarly here, we are saying that if dot is in certain position, that means what I have seen on left of dot and what I am going to see on the left of dot, on the right of dot, that is going to determine whether I have to do a shift or reduce, and if I have to do a reduce, then which rule I should use for reduction. If I can answer that, then I have a pass.
So should we check all the production?
Should we?
Check all the production.
Eventually we will have to, somehow. Okay? But right now, no. Right? Right now I don't have a parse table. Once I create a parse table, then I will not have to check everything. Then I will be able to deterministically say that take this action. Only one action. No backtracking.
So that step in which we reduce, do we shift in the same step?
We will shift in the same step.
So I mean, like here in the first step.
So what is the first step? Let's see.
So in which B is getting reduced to A.
This one?
So after one.
Here B was getting reduced to A, and then?
So are we shifting the dot in this step?
Not shifting. I mean, reduction is one action, shifting is another action. These are two separate actions. So when I said that my dot was here, dot will remain here. Right? So what I have done is, I found a pattern which is on the immediately left of dot, and I found that pattern matches right hand side of production, and I just replaced that by its left hand side. Similarly, when I found that on the left hand side of dot there is a pattern which matches a particular production, then I just replaced that and I kept the dot here. Okay? What I have not shown in between is that from this I must have done this shift before doing this reduction. So these are two separate actions. I either do a shift or I do a reduce. So let's do one thing. Let me take an example, take you through a full set of shift and reduce, and then we'll come back to this answer. Okay? So shift reduce parsing is, it will have two actions. Either I can do a shift which says move terminal symbol, which is on the right hand side of dot to the left hand side of dot. So if this is my configuration, which says alpha dot PQR, then after shift this is going to be alpha P dot QR. So P has been shifted on left of dot. And then I have a reduce action which says that if I match something which is on the left hand side of dot, and this pattern matches right hand side of a production, then I am going to reduce. So if this is the pattern I have which says alpha beta dot PQR, and beta matches right hand side of a production, then, and the production is A going to beta, then my configuration will be alpha A dot PQR. Okay, so this is what my reduce action is. So in this case I have reduced beta to A, in this case I have shifted P to the left of dot. Okay. These are the only two actions I have, there is nothing else. Okay. So I will keep on doing these mix of shift and reduce till I reach either the start symbol or an error state. Start symbol means that I am in the accept state saying that this is a valid string, error state saying this is not a valid string. These are the only two conclusions I can get. Okay. So let's look at this example and try to parse this particular string. Okay. So again, I'll just try to work it out for you so that you can at least get a feel for what is going on. Okay. And what we have is, we're trying to say that I have ID star ID plus ID. Okay. This is my start string, and my dot is here. Okay. And the grammar is on the top, it says E goes to E plus E, or E goes to E star E, or E goes to ID. Okay. So what I'll do now is, first I will do a shift. So my action is shift, which says that it now becomes my string becomes of this configuration. Okay. And then I do a reduce, okay, because I find that immediately on the left of dot there is a pattern which messages right inside of a production. So my reduce is by action saying that ID gets converted into E and my configuration remains this. Okay. Now once again I do a shift action and I say that E star dot ID plus ID is the configuration. Okay. And then I do one more shift, okay, and this shift takes me to a configuration like this. Okay. And then I do a reduce action which says that, so let me underline whatever I am matching when I do a reduce action. So here is an ID. Before I went to reduce action, here is one ID which I will now do using a reduce action, and then it takes me to something like this. Okay. Now I have a choice, okay, whether I want to shift or I say that E star E matches right hand side of a production and therefore do a reduce action. Right? So what I decide at this point of time is that let me do a reduce action. Okay? I am not telling you why I am making this choice, why I am reducing instead of shifting. Okay? But let's assume that this is the action I take, then what happens is this becomes my configuration. Okay? And then I shift once again, okay, and shift action gives me a string like this, okay, and then I once again shift, and this shift gives me this configuration, and then I decide that I want to do a reduce, okay, and if I do a reduce, this gives me E plus E, and then I want to do one more reduce action matching this, okay, which gives me now E dot, okay, and E is my start symbol, dot is immediately on the right hand side, so I say this is a valid string which I have identified through an action of shift and reduces. Okay. Now you can also see in this case, okay, suppose when I had this choice of saying that rather than doing a reduce here, I did a shift, what would have happened? Would I have reached this state finally? So let's try that. What was the second alternative? In this case, when I was doing, so let me say that I am in this state, okay, which is E star E dot plus ID, okay, and rather than doing a reduction, I do a shift, okay. So if I do a shift, what will happen? I will get something like this. I do one more shift, and that takes me to this state. Now I do one reduce, and reduction is now on this. So this gives me this configuration. Then I do one reduce, which says I match this as the right hand side. Okay. And remember that matching I always want to do immediately starting on the dot position. Okay. So I will not find a string like E star E and I will say I will match that, but I will always find a string which is immediately on the starting from left of dot. Okay. So this will give me this reduction, and then if I now do a reduce, that still gives me E dot. So I would have reached the same conclusion. Okay. Whether I did a shift or I did a reduce. Okay. Now, you almost have an idea perhaps, okay, that why this would have led to the wrong things, and this is the right set of steps I took. So is the second set of steps correct or the first set of steps correct? And why? Because of precedences. Okay. You find that if I am trying to, if I know that this is multiplication and this is addition, then this has higher precedence, and I want to make sure that this gets evaluated first okay, before this. And therefore, if I follow this sequence, then I am doing things in right order. If I follow this sequence, although I will reach the start state and I'll say this is a valid string, but I would be doing computations in some wrong step. And therefore, I feel really pinch at the time of code generation. Then I'll say that my code is incorrect. Okay. So I somehow need to take care of all my precedences and associativities also while specifying my grammars. Okay. And so here is what we have just gone through, that finally I reach this E dot step and I say this is accept. I'm just doing shift and reduce actions. Okay. Now trick here is, as I said, that when I start with this string, when to do a shift, when to do a reduce, and then which rule to use for reduce. If I can answer that, then I have a parser. Okay. And my whole algorithm is going to be based on what equivalent to, if I try to look at top-down parser, equivalent to saying the first and follow set computation, I'll do some pre-processing here, I'll do some similar computations and try to take this grammar and encode it into a parse table so that I can always deterministically take that action, which will tell me that whether I am doing shift or reduce. Is it beginning to sink in now? At least somewhat more clear than when we started with. Okay. So continuing on shift reduce parsing. Okay. Now let's also simultaneously start talking about the implementation. Okay. So whatever is on the left of dot, I can keep that on the stack, and whatever is on the right of dot, that can be my input state. And dot really is nothing but the input pointer, and that is also telling you what is your look ahead. So look ahead is going to be the symbol which is immediately on the right hand side of the dot. Okay, that is the first symbol you will see in your input. Okay, and top of stack is always corresponding to this dot, and shift pushes a symbol which is a terminal symbol on the stack. And what does reduce do? Reduce really takes something which is immediately after the dot or left of dot, which means which is on top of stack, which matches right hand side of a production. And if it matches right hand side of a production, what action do I take? I am going to pop all those symbols and I am going to push the left hand side on the stack. Right? This is what I am doing here. That when I say that E plus E matches right hand side of E star E matches right hand side of a production, I am going to pop these three symbols from the stack and I am going to push E on the stack. That is what my reduce action is. Okay. So this is what we do, and the most important issue we want to raise here is when do we want to shift and when do we want to do a reduction. Okay. So reduce action should be only done when we know that, and this is where now let's start thinking about the first example I gave. Okay. That there was a situation where I was doing a reduce action on B, reducing that to A, and that led to a block saying I cannot proceed, and I came to a conclusion saying that this is a wrong string. But if I did the right set of reduce actions, then I was able to reach the left hand side, okay, which is the start symbol. So therefore we are saying that reduce action I should take only if the reduction is going to take me somehow to the start symbol, if it's a valid string in the language. If it's not a valid string, then it doesn't matter. It will never take you to the start. Okay. So this is somehow this is a fact which needs to be captured somehow when I start creating my parse table. Okay. So let's look at some of the properties of bottom-up parser before we go any further. Okay. One, that this is more powerful parsing technique as compared to the top-down parser. Okay. And this class of grammars is known as LR grammars. It is more expensive than LL1 or equivalent LL. And when I say expensive in terms of creating the parse table. Okay, I have to put in more effort to create the parse table. Parse table also is going to be larger. It is going to occupy more space. Okay. As far as parsing itself is concerned, that is going to be still the linear time. I will not do any backtracking. Okay. So it's more expensive than LL1, and therefore, from trade-off point of view, you can see that it can not only handle left recursive grammars, but it can handle almost all programming languages. And therefore, this also remains the method of choice for creating parsers for most programming languages. And also, it is a natural expression of writing the programming syntax. So, for example, when I had these left recursive grammars like E going to E plus P or P, okay, my top-down parser was not able to handle that, and I had to rewrite my grammars into this form. Okay, so let me just write this form. Now you can see that if you read this grammar, okay, it's not very natural to figure out that what we are talking about are part of the expression grammar. If I read this, I can immediately figure out, okay, what I am talking about. Okay. So this is a much more natural way of expressing a language than this kind of notation, which is non-left recursive. Okay. Because bottom parsers can handle left recursion. That will not be an issue for them. Okay. Also, there are tools available. In fact, the first tools which were made, first automatic parser generators, were made for bottom-up parser. So YAG is a prime example, which was perhaps the first tool for bottom-up parser. Also, another interesting thing is that when it comes to error recovery, bottom-up parsers guarantee that it will never do a wrong shift or reduce. Okay. The class of bottom-up parsers which will immediately catch an error as soon as we go encounter, rather than saying discard certain symbols, the error recovery method we looked at. Okay. In this case, we will immediately be able to pin that down, okay, and therefore it will always lead to better error recovery. Okay. So these are some of the properties. Okay. But as we go along, you will find that we will be able to then look at these properties, and these properties will just stand out as we construct the parser. Okay. Now let's also simultaneously look at what are the issues I may face in a bottom-up parser. Okay. So the first question, which you have not answered, is that is when to shift and when to reduce. Okay. So in this case, I was doing a reduce, and in this case, I was doing a shift. I should be able to clearly answer that, and then I should also be able to say that which production I want to use for reduction, because there may be situations where I may have more than one right-hand side matching of a production. Okay. So sometimes I can have this reduction which says x goes to epsilon, which can always be done, okay, but we don't want to do that. Okay. So this question needs to be answered very clearly, okay, and sometimes parser can reduce in different ways, like here. Okay. It can reduce in different ways. So what you have to remember here is that if I take stack, okay, so look at it this way. So let me just explain this point, and then because when I'm doing, I think let's keep this example, I'll go on that side. Okay. So there's an important example which is a running example for us. So suppose this is my stack. Okay. It has lot of symbols. Now when I say that I am matching right hand side of the production, suppose this is top of my stack, okay, I can say this matches right hand side of the production and this matches right hand side of the production. Okay. My grammar can have such patterns. Okay. That means somewhere I'll say that if my stack is containing some string delta, which is a string of terminals and non-terminals, I want to divide this into two parts. Okay. And this really is, in one case there is a division, in another case there is a division. Okay. So what is the right kind of division? Okay. This my parser needs to answer. Okay. So this basically is saying that suppose I say that delta is my stack configuration and input symbol is A, then shift obviously will give me delta A. Okay. But when I say reduce, okay, reduction can happen that I can either take this part which matches right hand side of the production, or I can take this part which matches right hand side of the production, and this my parser will have to figure out. Okay. So what we start doing now is that how do we keep track of what is the length of this? So if I say that I can have a combination of alpha and beta and multiple combinations, then how do I keep track length of this? Okay. Whether this is the right size or this is the right size. So what we'll start doing now is we'll start giving some definitions so that at least we start building the parser. So after raising all these issues, let me give the first definition. Okay. And that is what I call as handle. Okay. And handle is something which has two properties. So handle is right hand side of a production. If I now look at this, okay, so what I was really doing was I was matching this ID, okay, I was matching this ID, then I was matching E star E. So handle is something, a string that matches right hand side of a production. And the second part, which is more important, is that if I replace this right hand side of a production, then it is going to give me a step within the reverse of rightmost derivation. Okay. So unless these two conditions are satisfied, something cannot be designated as handle. So this was precisely the problem. If you recall that first situation I had, first situation was I started with this and I said this matches and I replaced this by its left hand side, and then I erroneously said I am going to replace this by its left hand side. Okay, so it matches right hand side of a pattern, but if I look at the reverse of rightmost derivation, then this replacement was not giving me the reverse of rightmost derivation, and therefore this was the wrong choice. Okay, and therefore now if I want to define my shift reduce parsing in terms of handle, I can say keep on identifying handle and keep on replacing handle by its left hand side. If I keep on doing that, because I am doing now, what is the handle now? This is saying it is going to give me a step in the reverse of rightmost derivation, so eventually it will lead me to the start symbol. So, okay. Now today things don't seem to be registered. See, if something is not clear, you need to raise a question. Because, I can make out from your faces that you are not understanding, but I do not know what is it that is not clear. So, unless you ask a question, I will have no clue of what is not clear.
So,
Yeah.
so this rightmost derivation is the expected rightmost derivation of the string. So,
No, there is nothing like expected rightmost derivation. There is a rightmost derivation of this.
so there is a unique pathway from S to W.
Yes.
But we don't know that from, before we start parsing, we
We
don't
don't.
know that.
We don't.
So how can we say that replacement was not a
I am not saying, I am just giving a definition. I am not giving you a method, is it? Right? What you are talking about is a method. So somehow this information will have to be captured in the method. That each time I do a reduction, somehow that is going to lead to a reverse of rightmost, a reverse step in the rightmost derivation. Yes.
So suppose in that previous example, the input string had been ID plus ID star ID.
ID plus ID star ID.
Yeah,
Okay.
then according to the same rules, we would have taken ID plus ID to be an expression, and then its multiplication with the expression.
Hmm.
But that would have defied the laws of physics as well.
Why do you say that? So let's look at this. So if this is the string you're saying, okay. So what will I do? Okay. What I'll do is I'll start from here. I'll shift this, okay, and then I'll do a reduce. Then I'll shift this. Then I'll shift this. I'll do a reduce, and then I'll do either a shift, continue to shift this, and then shift this, do a reduce, then replace this and replace this.
Which one is right? So like E plus E, we are reducing E plus E to E, or so we will shift again to that.
So you tell me which is right.
So one will
I have multiple choices here, right? So one of them is wrong.
If we shift, then it will be according to rightmost, but it will not break the precedence left to.
So that means this grammar is not in a form where I can generate strings without any problem. And what is the problem here? So what was the problem when I had more than one leftmost derivations? What was that problem called? Ambiguity. So I have the same problem here. So in bottom-up parsers, it's not that I don't have ambiguous grammars. This actually is an ambiguous grammar. So I want to make sure that my grammar is in a form, okay, and therefore I wrote that E goes to E plus P. My grammar is in a form where it's not ambiguous whether I do a leftmost derivation or a rightmost derivation. But my grammar is ambiguous, then I can always come up with more than one parser. But that's not taking me anywhere, right? So I need to make sure that in case of ambiguous grammars, I somehow define in my parser saying that this has higher precedence than this. Okay, and therefore, when I had this choice between either doing a shift or reduce, then I make the right choice and say that no, don't do a reduce, do a shift first, and then do reduction. That would have resolved the problem. So the problem was something like this. Suppose my configuration at some point of time was this. This would have been the configuration after some time. Okay. Now I have a choice saying that either I do a reduce or I do a shift. Okay. But because I defined somewhere that this has higher precedence than this this would have resolved in favor of a shift. And a shift would have led to situation like this. And then if I do a reduction here, this is the right reduction.
Please give an example of how we can give precedence in the group.
How can I give?
Precedence in grammar.
So you don't give precedence in the grammar. You use some tool to give a precedence. Otherwise, I said the method should be rewrite the grammar so that you don't have ambiguity. It will always give me only one leftmost derivation or only one rightmost derivation. Okay? And therefore, I am writing my grammars all the time, which is in this form. Right? This grammar is not ambiguous. This will always give you only one leftmost or one rightmost derivation. But if I write grammar like this, then in grammar I cannot write it, but if I use a tool, then I will be able to use something like this. Okay, and which said that these have same associativities and this has higher precedence than this. But this is part of a tool, not part of the grammar. The grammar is ambiguous. Okay, and therefore, best method I said was write grammars which are unambiguous. Right? This is the first thing we talked about when we discussed grammars.
So in that example, the ABCD,
Mhm.
how did you say that the second key reduced to was
Because it matched. Because, yeah.
it was not the right side of
No, it was right inside of a production, right?
rightmost derivation, not the
But it was not in the reverse of rightmost derivation. I showed you the rightmost derivation. Shall I go back there? Okay, let's go back to that foil once again. Yeah. So this is the rightmost derivation. Right? And if I just start doing reverse of rightmost derivation, if I reduce this b to a, then that will not give me a step here. Okay. But if I do this reduction, that is giving me a step here, right? Just a, b. So this is the reduction, this is the derivation. This is the rightmost derivation.
So still we do not have a way to find out what the correct rightmost derivation was. Where we look for the
No. In this case, there is only one rightmost derivation. It's not a question of correct rightmost derivation. Look at this. Can you find any other rightmost derivation for this?
This is basically a top-down parsing.
This is not top-down parsing.
No, this right, the derivation. When we find out the string from the start symbol,
Yes.
then we say that this is the rightmost derivation, and we check here whether something is in the reverse of this.
No.
So
No. Please don't confuse between the method and the definition. Right? So I'm saying that if I remember this fact, that whenever I do a reduction action or I do a shift action, that should lead me to reverse of rightmost derivation. Does not mean that I'll first do a rightmost derivation and check it. I can always devise a method where I can take this grammar, and when I convert this into a tabular form, okay, this fact is captured there without doing rightmost derivation.
we checked it through a derivation only.
No, we did not check it through derivation, please.
How did we intuitively do that?
Because I have not shown you how to construct the parse table. When I construct the parse table, this fact somehow will be captured in the parse table. Okay? That what is the right handle. See, ultimately, what I have to do is, so let me go back to the last foil, what I was just showing. Okay? Handle. Okay? So here we are saying that a string that matches right hand side of a production and whose replacement gives a step in the rightmost derivation. Okay? That means if I can have a method which is capturing this information into identifying a handle, then the job is done. Then I don't have to worry about rightmost derivation. So somehow this becomes part of your construction of the parser, not when parser is actually parsing a string. Yes? Okay?
So,
Yeah.
so if I start the dot from the right hand side, then it
Wait. You can it's not that you can start dot from the right hand side or in the middle or anything. Right? There's a method. Okay? And we always scan our input from left to right. So I am not scanning my input from right to left. Okay? So you cannot start from an arbitrary place. Wait. You're going into a territory which you have neither discussed or for which we don't even have proofs. So it's not symmetric first. Look at it this way, that I defined the concept of a lookahead symbol when I was reading it from left to right. Yes. Now can I say the same thing about reading from right to left and say that rather than lookahead symbol I have a tail symbol? No. So symmetry does not apply here really. So let's stick to the method and not say that I can put dot anywhere arbitrary in any arbitrary place and if I start from there. Then you can say that why go through this parsing method? I am talking about a specific parsing method. There are other parsing methods, okay, which will not even worry about dot, okay, which will give you all possible parse tables and which will say that doesn't ambiguity is not an issue because I use n-cube algorithms and I will give you all possible parsers. There are parsers like that. Okay. But we want to discuss a parser which in a single pass in linear time will give me whether a string belongs to the language or not. So I am discussing that method. I am not talking of any parsing method in the world. I am talking about a specific parsing method which is a bottom-up parser which falls in the class of Ella. Okay, so there is a parser called Early's parser which gives you all possible parses, but that takes n-cube time in terms of number of symbols. When parser runs, not when parser is constructed, when parser runs, because it is giving you all possible parsers. So it will keep doing that trend, and we will keep on saying, okay, this is a possibility, here is a possibility, here is another possibility. Now you choose. So natural languages where you do not have such clean interpretation of the precedences and associativities, they may have, depending on the context, they may have different associativity. We try to use those parsers, but in programming languages we don't. So let's do one thing. Okay, I think we'll have to do it in two passes. Okay, let's move slightly ahead and then keep coming back till this issue gets completely resolved. Okay, because if we get stuck at a point, okay, we may not be able to at this point of time if it is not clear. Okay, at least by taking an example, it will become somewhat clear. Bottom-up parsing, LR parsing, always is an issue. It takes time to sink in, but once it sinks in, then you'll be fine with it. Okay. So let's look at what a handle is, and what we are saying is that if I say that I am doing a rightmost derivation, what that handle means is that if S in a step of rightmost derivation takes me to a configuration which is alpha AW, and then one step of rightmost derivation says that since W is a string of only terminals and A is the first non-terminal on the right hand side, if I see from the right hand side, and there is a production which says A goes to beta, then alpha AW gives me alpha beta W. Okay. So this is the rightmost derivation, and the reverse of rightmost derivation will be that I look at beta and replace it by E. That will be the reverse. Okay. So in this case we say that beta is a handle. So beta is not a handle arbitrary, but beta is a handle only if such a step is possible in rightmost derivation. Okay. So for example here, this B is a handle, but this B is not a handle. So it's not that something matches right hand side becomes a handle, but it should also fulfill this property that it should give me this step. Okay. So let's take a break here today. I'll just finish this. Okay. So what we want to do is we want to reduce only handle and not any right hand side. Okay. And then what is handle pruning? Handle pruning is saying that if beta is a handle and A going to beta is a production, then replace beta by A, and a rightmost derivation in reverse can be obtained by just by handle pruning. Okay. So the question now is, in a bottom-up parser, how do I identify a handle? Because if I can identify a handle, then my job is done. Okay. So whole construction of bottom-up parser is through handle pruning and by method of identifying a handle. that is something we'll start discussing tomorrow, and then we think by this weekend we'll be able to finish at least one version of bottom of pass. Okay, so let's break here today, and then we continue our discussion from tomorrow.